Yeah, so today I wanted to demonstrate buffer overflows, how to exploit it. So I'm going to use a challenge that's actually running right now that I just solved. It's called Nothing More to Say, here from the Western Tokyo CTF. There are two files, the C file and the executable. So I downloaded them both here into this directory. See, the binary is here. It's a 64-bit ELF binary for Linux. Okay, so we can look at the C code, see what it does. It calls init.proc and does some buffer magic. There is a buffer here which is 100 hex bytes long. It puts a string to stand it out. Then this is the dangerous function that doesn't do any boundaries check, so it just reads a string from standard in until new line is found or end of file is found, and writes it to the address we provide here, which is this address, and we have only reserved 100 hex bytes. So if we write more than 100 hex bytes, we will overwrite the stack. And what happens then is that, well, on the stack is the return pointers. So when the program comes here to this end of this main function, it wants to return to the calling function, which is something that calls main in every C program. But it will not return there because we have overwritten. So we can jump wherever we want. Where do we want to jump to execute our shell code? Where there's some description here how to do. The binary has some protections disabled and some protections enabled. We can actually see what's enabled and disabled clear here. So if I start it here and then I can just see the memory maps of this process. So you can see this looks kind of random. These addresses here to the address to libc and address to the stack and so on. But these where the code is, and this strange page, which actually has read, write and execute permissions, seems to be static address. Let's run it again and see if it's actually static. Check 601 and 602. And this 7FC6. Run it again. And see, this has changed, but this has not changed. Those three are the same. Those three memory ranges. So here is where we want to put our shell code, in this memory segment. But how do we do that? Well, if I check the C code again, here we can overwrite the return pointer, jump to wherever we want, including jump into the code itself. So what I want to do is to jump into the code itself and call get again. But this time, when I call get, I want it to write the next things it reads from standard input. I want it to write into a specific address, that read, write, execute page. Alright, and then I want it to jump into this read, write, execute page. Okay, let's first find the offset. And pipe it to the binary. And it crashed and the core is dumped. Now we can't see much, but add a couple of more bytes. And now we should be able to see something with GDB. So if I start GDB, now I just want to watch the core. GDB, warm up, core. Now we can see that it crashed in an address that ends with 4141. and 41 is the big A, hexadecimal code for it. So we can see that we overwrote the return address with 2 bytes and it made the program crash. So if I just remove 2 bytes from this offset, 10A to 109, 108 here, these many bytes I have to fill up until we get into the return address. And then if I want a full exploit, I want to do this first and then add the address of the gadget, and I want to add the memory address, and I want to add the gets call address, and I want to all add the memory address again. And boom, and then pipe this all to warm up, and we should get the shell. So this is not the correct syntax to do this. To do it, I'm going to use something called pwntools. So that's a Python framework for writing exploits. I use Python 2 and import the module pwntools, which is written by a CTF team. I think it's called, they are called Gallops. Okay. Now pwntools can do this cool thing that actually generates shell code. So I'm going to cut and paste the code to generate the shell code. It looks like that. First I specify the architecture, and we checked with the file. It's 64-bit Intel, which is in pwntools called AMD64, and the Linux operating system. And shellcraft.sh generates assembly code, and OSM calls an assembler to actually assemble this and create shellcode that can be put into somewhere in the memory, and then we could jump to that address where the shellcode is, and we should get the shell. So the offset was 108 hex. We could then add something more. Did we check the memory addresses? The RVX page is at address here. I can put that in the Python code too. Alright. What do we need more? I can have this open. We need the address of the gets call. So it's 400,580 seems to be the thing. And where is it called? Here in here in main. It's all 400,580. So here is the address of the gets call. So if we just jump directly to this address, and this address is static. Every time we execute the program, it will be at this address. It gets call. So this code here jumps into libc and execute gets. Pointer to gets is alright. And what do we need more? Yeah, we need one more thing, because on 64-bit Linux, the first argument to gets is in register RDI, but on 32-bit the first is on the stack. So we have to insert something, code that loads from the stack one address and puts it in register RDI. And I can do this. Now see, tools, let's see, I think I put it in ROP gadget. And ROP gadget.py, and it's Python 2. default is Python 3. Binary warm up. Let's see what this does. So if we look through, these are sections of the code or addresses in the code, which you could also find with obdump, that could be useful when writing an exploit, and each such address is called the gadget. So the gadget we need here is load one address from the stack into register RDI and return. And what return does is load an address from the stack and jump to it. So this is exactly what we need, and that is happening at this address. So I copy that. So these are all the data we need, and the rest is basically the same for all exploits. First, we call a process, and this could be either a binary that's local on our computer, or a call to a socket to a remote server. So the only thing to do is to change this line to switch between the local binary and the actual server running remote. So I comment this out for now, but when the exploit works I can comment out this line and instead use the real address. Now I'm just using my local binary on my local disk. Alright, and what happens when we run it? Well, it prints some information until we get to this line. So we should actually wait until this line is reached. Here. So receive until just receives data from the server or from the local process until it sees this string, and then it stops. And what should happen after that? Well, these numbers here, this number is okay as it is, but those three numbers have to be changed to little endian and 64-bit little endian, and in pwntools there is a handy little function called p64 that does this. So I'll just convert those three to little endian and put them in new variables. Boom, like that. Gadget, mem, android, and pget. So now we have the payload, which I went through earlier. I'm just gonna paste it from a working program. Let's see if it works then, after my cut and paste exercise. So first I just write a lot of big A's, 41 hex, offset number of big 8s. Then I write the gadget address, and the gadget, what did the gadget do? I can write what it does. It loads from the stack one address into register RDI, and then it calls return. After I send the payload, then sget will be finished and the program will continue to execute, and when it hits end of the main function, the stack will be overwritten with first this gadget, and then this memory address, and then this address of the gets call of the program, and then the memory address again. So first it will jump to this address, gadget address, that pops one address from the stack into register DI and returns. So this puts this address into register DI, and then it jumps to this address, the call to gets. Gets loads one line of code of ASCII characters from standard input and puts it on the address that is specified in the first argument, and that is in register DI. And with these lines we have put the RVX page into register DI. So if this returns, it will load the return address from the stack, and here we put the return address from the stack. It's the same address where we loaded our shell code, so it will jump to this address here. Now what do we want to do next? Well, what happens after these two lines and gets? Well, then the program will call gets and wait for code. So we have to send our shell code. And we actually don't know how much time we should wait, but yeah, we could sleep 1 second, but maybe it works without sleeping 1 second. So I'll just send the shell code. And if everything worked, it should pop a shell. And if it popped the shell, pwntools has these interactive functions that lets us interact with the shell. And this close is not really necessary, but we can call close if we want to. Let's see if this works. It didn't work because send line is not defined. Why is send line? Aha, it should be p.sendline. All right, what happened here? It looks like we got the shell. Yeah, I got the shell on my local process. In reality, it took a little longer time. So now let's just change one line and then connect to the actual server. And the contest is not finished yet. It's 4 hours left until finish. So the server, contest server should be live. Let's see. This should be exciting. Just edit this. Comment out this local binary and connect to the actual CTF server on port 10,001. ls, there's the flag, cut flag, boom, and we got the flag.